The environment enclosed within the cylinder of an internal combustion engine is one of the most hostile thermodynamic arenas ever constructed by human engineering. During a standard operational cycle of a high-performance vehicle, a piston compresses a precisely atomized mixture of hydrocarbon fuel and atmospheric air, driving the internal pressure to hundreds of pounds per square inch. At the exact millisecond of maximum compression, an electrical management system forces a current carrying tens of thousands of volts across a microscopic gap between two metallic electrodes. This event is not a simple transmission of electricity. It is a violent, localized tearing of the gaseous medium. The extreme voltage ionizes the compressed air-fuel mixture, stripping electrons from their atomic orbits and creating a channel of superheated plasma. This plasma arc, commonly known as a spark, bridges the gap and can reach localized temperatures exceeding 10,000 degrees Fahrenheit.
This thermal peak is momentarily hotter than the visible surface of the Sun, and it serves as the ignition source that drives the explosive expansion of gases required to propel the vehicle forward. However, this microscopic lightning bolt is incredibly destructive to the structural integrity of the metallic electrodes themselves. The generation of a plasma arc involves a phenomenon known as electrical ablation. The intense thermal shock, combined with the electromagnetic force of the arc, literally boils away the metal atoms from the surface of the electrode, eroding the material with every single firing. A standard engine running at cruising speeds will demand thousands of these plasma detonations every minute. If the electrodes are constructed from conventional industrial conductors, such as copper or nickel alloys, the surface of the metal will rapidly degrade. The intense heat causes the metallic lattice to destabilize, and the electrical force blasts the loosened atoms into the combustion chamber. Over time, this constant erosion widens the physical gap between the two electrodes until the electrical system can no longer generate enough voltage to jump the distance, resulting in a misfire and the subsequent failure of the engine block to produce power. To construct a propulsion machine capable of surviving millions of these localized plasma detonations without suffering a loss of efficiency, engineers must utilize a material that operates at the absolute outer limits of physical and thermal endurance. Hidden at the very apex of these high-performance spark plugs is a microscopic, precision-welded disc of the 77th element in the periodic table. This element is iridium, a substance characterized by a degree of structural cohesion that renders it practically indestructible under terrestrial conditions. The utilization of iridium in this violent environment is not a matter of aesthetic luxury or commercial prestige, but a rigid necessity dictated by the laws of physics. Its presence allows the spark plug to be engineered with an extremely fine, needle-like tip, which concentrates the electrical field and generates a more efficient, powerful arc, while enduring the inferno of the cylinder for hundreds of thousands of miles without requiring replacement. The extreme resilience of iridium is a direct consequence of its extraordinary atomic architecture. It stands as the second densest element known to science, possessing a mass of 22.56 grams per cubic centimeter. To translate this metric into a tangible physical reality, a standard cubic foot of solid iridium, representing a block small enough to easily rest upon the seat of a common kitchen chair, would weigh over 1,400 pounds. This staggering density is the result of 77 protons and a tightly packed cloud of electrons being compressed by massive nuclear forces into an incredibly small atomic radius. Within a solid piece of this metal, the atoms are organized into a face-centered cubic lattice, a specific geometric arrangement that maximizes the number of strong metallic bonds each atom shares with its immediate neighbors. The strength of these internal connections is unparalleled in the material world. In the vast majority of metals, an influx of thermal energy causes the atoms to vibrate violently,
eventually overcoming the forces that hold the lattice together. The atoms begin to slide past one another, resulting in the metal softening, yielding, and ultimately melting into a liquid. In iridium, the specific configuration of its outer electron shells, specifically the densely packed d orbitals, acts as an incredibly rigid internal scaffolding.
It requires a colossal input of thermodynamic energy to disrupt this lattice. Iridium possesses a melting point of 4,435 degrees Fahrenheit, a thermal threshold that vastly exceeds the temperatures that would cause standard structural steel or titanium to liquefy into useless, glowing slag. The metal remains entirely solid and structurally sound in environments where other materials simply cease to exist in a cohesive state. This extreme atomic density and binding energy also endow iridium with a level of chemical inertness that borders on the absolute. In the discipline of material chemistry, the reactivity of a metal is generally evaluated through its vulnerability to aggressive acids. Hydrochloric acid or nitric acid will rapidly dissolve common metals like iron or zinc by stripping away their electrons and dismantling their crystalline structures atom by atom. For the most resilient precious metals, such as gold and platinum, chemists utilize a highly corrosive, oxidizing mixture known as aqua regia, or royal water. This fuming combination of concentrated nitric and hydrochloric acids is capable of tearing apart the atomic bonds of gold, dissolving the solid metal into a liquid solution. Iridium, however, represents a thermodynamic wall that even aqua regia cannot breach. If a solid bar of iridium is submerged in a boiling bath of this highly aggressive acid mixture, the acid will have absolutely zero effect. The dense packing of the iridium atoms and the high activation energy required to remove its shielded outer electrons present an insurmountable barrier to the acid molecules. The corrosive compounds simply cannot find a weak spatial point to attach to, nor can they exert enough electromagnetic force to steal an electron away from the iridium lattice. The metal remains completely unaffected, sitting at the bottom of the boiling acid bath with the exact same pristine silver-white luster it possessed prior to the exposure. This absolute refusal to engage in electron exchange or form chemical bonds makes iridium the most corrosion-resistant metal on the periodic table, an element that functions as if it operates in a vacuum, entirely isolated from the reactive chaos of the atmosphere. The application of this indestructible material is not limited to the high-voltage interior of an engine cylinder. It is also concealed within objects of refined domestic elegance, specifically the nibs of high-quality fountain pens. Writing with a fountain pen is often perceived as a delicate, frictionless operation, but at the microscopic level, it is an act of continuous, abrasive destruction. Standard writing paper is a composite material, manufactured from intertwined cellulose fibers, often heavily coated with microscopic particles of silica, clay, or calcium carbonate to provide a bright, smooth finish. When a metal pen nib is dragged across this surface to deposit a trail of liquid ink, it is effectively being dragged across a continuous sheet of very fine, mineral-coated sandpaper. Over the course of years, as the pen transfers miles of ink lines onto paper, the unrelenting friction will grind down the tip of a standard gold or steel instrument. The metal will be slowly shaved away, causing the tip to become blunt, uneven, and scratchy, ruining the capillary action required for smooth ink flow. Furthermore, the inks utilized in these instruments are complex chemical solutions that are often mildly acidic or alkaline, creating a continuous chemical exposure that can pit and corrode lesser metals. To ensure that a premium writing instrument can function flawlessly for a lifetime, manufacturers utilize the unparalleled endurance of the 77th element, a microscopic sphere composed of an alloy that is primarily iridium and its dense neighbor osmium, is precisely welded to the very tip of the gold nib. Because iridium possesses an immense mechanical hardness that ranks far above platinum or gold, it totally resists the abrasive grinding of the paper's mineral fibers. The atomic lattice of the iridium tip simply refuses to shed its atoms under the mechanical stress of writing. Simultaneously, its absolute chemical inertness guarantees that it will never rust, tarnish, or degrade, regardless of the aggressive chemical composition of the ink flowing over its surface. This tiny, nearly invisible fragment of metal ensures the physical integrity of the instrument, allowing it to perform a delicate task for decades without a single measurable alteration in its geometry. This same unyielding physical and chemical stability is the precise reason the international scientific community entrusted iridium with the most critical and foundational measurement standards in human history. For over a century, the global definition of mass and length was physically tethered to objects housed in a high-security, climate-controlled vault outside Paris. The international prototype of the kilogram and the international prototype of the meter. These were not mere blocks of metal. They were the absolute, unquestionable references upon which all global trade, aerospace engineering, and advanced scientific calculations were based. If the physical mass of the reference kilogram fluctuated by even a single microgram due to oxidation or wear, the mathematical foundation of global industry would be compromised, leading to microscopic but compounding errors in everything from pharmaceutical dosages to satellite trajectories. The material chosen to bear this immense responsibility was an alloy composed of 90% platinum and 10% iridium. The inclusion of iridium in this alloy was an absolute engineering imperative designed to halt the passage of time. A pure platinum weight, while highly resistant to tarnishing, is relatively soft and susceptible to microscopic scratching or denting if handled or cleaned. By alloying the platinum with iridium, the resulting material acquired a profound structural rigidity and hardness. More importantly, the iridium-platinum alloy exhibits an extremely low coefficient of thermal expansion, meaning its dimensions do not significantly warp or shift as the ambient temperature changes. It also possesses a total immunity to atmospheric oxidation. It does not absorb moisture from the air. It does not react with trace sulfur compounds to form tarnish, and it does not absorb stray gas molecules into its lattice. The cylinder of metal sat inside a nested series of protective vacuum jars for 130 years, its atomic structure remaining perfectly static, providing an unwavering anchor of consistency in a world characterized by constant physical decay. The utilization of iridium in these absolute prototypes represents the highest functional compliment humanity can bestow upon a material, trusting it to define the very metrics of reality because it is the only substance that categorically refuses to be altered by its environment. The everyday paradox of iridium is thus defined by its simultaneous invisibility and its absolute physical superiority. It is a material that the average person will never hold in its pure, isolated form, yet it silently governs the performance of the most demanding machines and guarantees the accuracy of the most delicate instruments. It operates by the principle of total chemical exclusion, maintaining its structural identity by presenting a thermodynamic wall to the outside world. Whether it is withstanding the rapid 10,000-degree plasma detonations inside a racing engine, resisting the continuous abrasive friction of a writing desk, or ignoring the corrosive boil of concentrated acids, iridium performs its function by remaining completely and utterly unchanged. We have harnessed the most indestructible and unyielding metal in the terrestrial inventory, a material whose extreme density and thermal resolve hint at a violent cosmic origin far beyond the confines of the Earth, utilizing its uncompromising architecture to build the tiny, infallible anchors that hold the high-speed, high-precision modern world together. The absolute scarcity of the 77th element within the accessible crust of the Earth is not merely a geological coincidence,
but the final result of a rigorous, planetary-scale sorting mechanism that operated during the earliest and most violent epoch of the solar system. To comprehend why a material so critical to modern high-performance engineering is virtually absent from the standard mineralogical inventory of the planet, one must first examine the extreme astrophysical constraints governing its creation. Iridium is a member of the heavy platinum group metals, a classification of matter that cannot be forged within the steady, predictable nuclear furnace of a standard star.
While elements such as carbon, oxygen, and silicon are the mass-produced byproducts of stellar fusion, the creation of a nucleus containing 77 protons and over 115 neutrons requires an environment of thermodynamic and gravitational extremity that defies conventional stellar mechanics. This specific atomic architecture is the product of the rapid neutron capture process, commonly referred to as the R process. This phenomenon occurs almost exclusively during the catastrophic collision and merger of two neutron stars. These celestial objects are the ultra-dense, collapsed cores of dead supergiant stars, possessing a density so severe that a single cubic centimeter of their material would possess a mass of roughly 100 million tons on the surface of the Earth. When two such entities are locked in a decaying orbital dance and eventually collide, the resulting impact shatters the boundaries of standard physics. For a fraction of a millisecond, the collision environment is flooded with a concentrated hurricane of free neutrons moving at relativistic speeds. These neutrons strike the nuclei of lighter elements, packing into them with such rapid intensity that the atoms are forced up the periodic table before they have the opportunity to undergo radioactive decay. Iridium is born in this momentary apocalyptic flash, a high-energy heavyweight synthesized in the absolute margins of celestial probability. Following the collision, this newly forged material is violently ejected outward, scattering across the interstellar vacuum as a fine metallic dust, destined to drift for eons until it is captured by the gravitational pull of a forming stellar nebula. Approximately 4.6 billion years ago, a vast cloud of gas and dust containing these trace amounts of iridium began to collapse to form the local solar system. As the primordial Earth accreted from the swirling disk of planetary debris, it was subjected to a continuous and devastating bombardment by massive planetesimals. The kinetic energy of these colossal impacts, combined with the intense heat generated by the radioactive decay of short-lived isotopes, transformed the infant Earth into a global sphere of churning, low-viscosity magma. The planet existed in a state of total liquefaction, a roiling ocean of liquid rock and metal extending thousands of miles deep. In this fluid environment, the laws of gravity and fluid dynamics dictated the internal architecture of the world through a process known as planetary differentiation, or the iron catastrophe. Because the planet was entirely molten, materials were free to move and segregate based purely on their specific density and chemical affinities. Iron and nickel, being immensely abundant and significantly denser than the surrounding silicate magma, began to separate and sink toward the gravitational center of the planet. To explain this mechanism on the fingers, it operated much like a mixture of oil and heavy syrup that has been vigorously shaken and then allowed to settle. The heavier syrup will inevitably pool at the bottom of the container. Trillions of tons of molten iron descended through the magma ocean, forming the dense metallic core that currently resides at the center of the Earth. The fate of the planet's primordial iridium supply was sealed by its specific chemical behavior during this massive downward migration. In the discipline of geochemistry, elements are categorized by their preferred bonding partners. Iridium is classified as an extreme siderophile, a term denoting a profound chemical affinity for iron. At the atomic level, the outer electron configuration of the iridium atom makes it highly predisposed to dissolving into liquid iron rather than forming bonds with the lighter oxygen and silicon atoms that constitute rocky minerals. Consequently, as the massive droplets of liquid iron sank toward the center of the Earth, they acted as a planetary-scale chemical sponge. The iridium atoms readily dissolved into the descending iron, hitchhiking a ride down into the abyssal depths. The sheer density of iridium, which is more than twice that of lead, compounded this effect, ensuring that virtually every solitary atom of the 77th element was relentlessly dragged down into the core. It was locked away beneath 1,800 miles of dense rock, subjected to pressures exceeding 3 million atmospheres, rendering it permanently inaccessible to the surface environment. As the Earth gradually radiated its heat into space, the outer layers of silicate magma began to cool and crystallize, forming the solid rocky crust upon which all biological life and human infrastructure would eventually exist. However, because of the ruthless efficiency of the iron catastrophe, this newly solidified crust was swept entirely clean of its heavy, iron-loving precious metals. The surface of the planet was effectively an iridium desert. To quantify the magnitude of this depletion, one must examine the extreme statistical rarity of the element in standard continental rock. The average concentration of iridium in the Earth's crust is estimated at roughly 0.001 parts per million. It is so vanishingly rare that finding a single gram requires the processing of thousands of tons of raw earth, making it significantly scarcer than gold or platinum. If the geological history of the planet had concluded with the solidification of the crust, iridium would be nothing more than a theoretical ghost element to the human species, permanently entombed in the planetary core and entirely absent from our technological inventory. The presence of iridium in the modern industrial supply chain is entirely reliant upon a secondary sequence of cosmic events that occurred long after the Earth had formed its solid outer shell. This mechanism is often referred to in planetary science as the late veneer hypothesis. For hundreds of millions of years following the solidification of the crust, the solar system remained a chaotic and highly unstructured environment. The gravitational migrations of the giant outer planets, Jupiter and Saturn, disrupted the orbits of millions of asteroids and comets, sending a relentless barrage of rocky debris hurtling toward the inner solar system. This era, known as the Late Heavy Bombardment, subjected the Earth to a catastrophic rain of celestial impacts. These incoming asteroids and meteorites were distinct from the surface rocks of the Earth. Many of them were primitive chondrites, or fragments of metallic asteroids that had never undergone the process of planetary differentiation. Because these smaller bodies had never melted completely and formed their own separate iron cores, their heavy elements had never sunk to the center. They retain the original primordial mixture of elements present in the early solar nebula, including rich concentrations of gold, platinum, and crucially, iridium. When these massive celestial bodies collided with the Earth, the dynamics of the impact were fundamentally different from those that occurred during the planet's molten infancy. Because the Earth's crust had already cooled and hardened into an impenetrable shield of solid rock, the heavy metals contained within the meteorites could no longer sink into the core. The gravitational door had been permanently closed and locked by 1,000 miles of solid mantle. Instead, the kinetic energy of the meteorite strike instantly converted to thermal energy, vaporizing the asteroid upon impact and blasting a colossal crater into the surface. The material from the asteroid, including its payload of iridium, was pulverized into an atomic dust and ejected high into the atmosphere, eventually raining down and settling into the upper layers of the cooled crust. This mechanism reveals the ultimate paradox of the 77th element. The planet Earth is functionally divided into two distinct zones regarding this metal. The vast, unreachable reservoir of primordial iridium hidden in the core, and the microscopic dusting of secondary iridium scattered across the surface. Every single gram of iridium that human civilization has ever mined, refined, and utilized is a direct consequence of this delayed celestial delivery. It is a cosmic landing force that arrived millions of years too late to join the migration to the center of the world. When an engineer installs an iridium-tipped spark plug into a combustion engine, or a surgeon utilizes a microscopic iridium capsule for targeted radiation therapy, they are not utilizing a material that is native to the Earth's crust. They are employing an extraterrestrial import, a fragment of a wandering asteroid that was forged in the apocalyptic collision of two neutron stars, drifted through the dark vacuum of the galaxy for eons, and violently crashed onto the surface of this planet. The extreme hardness, absolute chemical inertness, and staggering thermal resilience of the metal are not just engineering specifications. They are the physical scars of its violent origin and its long, hostile journey through the cosmos. Iridium is the ultimate cosmic fugitive, a heavy, unyielding traveler that escaped the crush of the Earth's core, only to be scattered across the surface.
Waiting in the silent rock for a civilization advanced enough to recognize its unparalleled durability and harness the indomitable architecture of the stars. The formal recognition of the 77th element within the human scientific inventory is a narrative characterized by a prolonged period of chemical frustration, marking a unique instance where a material of supreme structural importance was initially categorized as a nuisance and discarded as industrial waste. Throughout the late 18th and early 19th centuries, the forefront of metallurgical science was dominated by an intense preoccupation with platinum. This heavy, silver-white metal had been identified as a material of extraordinary utility due to its resistance to corrosion and its high melting point, making it highly desirable for the construction of specialized laboratory equipment and standardized weights. However, the purification of platinum presented an immense operational hurdle.
The raw platinum ore, extracted primarily from alluvial deposits in South America, was never found in a state of absolute purity. It was always alloyed with a complex matrix of unknown, heavy contaminants. In the pursuit of pure platinum, the chemists of the era relied upon the most aggressive liquid solvent available to 19th century science: aqua regia, or royal water. The application of aqua regia is a process of extreme chemical destruction. This fuming, highly corrosive liquid is a precise mixture of concentrated nitric acid, HNO3, and hydrochloric acid, HCl. To understand the mechanical function of this solvent at the atomic level, one must examine a dual action mechanism of oxidation and coordination. The nitric acid acts as the primary oxidizer, possessing the chemical force necessary to strip electrons away from the surface atoms of the platinum. Once a platinum atom loses its electrons, it becomes a positively charged ion, detached from the rigid metallic lattice. Simultaneously, the hydrochloric acid provides a massive concentration of chloride ions. These negatively charged chloride ions immediately surround the newly liberated platinum ion, forming a stable, water-soluble complex known as chloroplatinic acid. Through this continuous, two-step cycle of electron theft and ionic encapsulation, a solid bar of platinum can be entirely dissolved into a bright orange liquid. However, during this rigorous purification process, an unexplained phenomenon consistently disrupted the expectations of the European laboratories. After the raw platinum ore had been completely subjected to the aqua regia and the liquid had been decanted, a fine, dark residue always remained at the bottom of the glass reaction vessels. This residue appeared as a dense, heavy black powder, entirely unaffected by the boiling, corrosive mixture of acids. For decades, the leading scientific authorities of the era assumed that this unyielding sediment was merely a form of plumbago, an archaic term for graphite. Because graphite is a crystalline form of carbon known for its extreme chemical inertness and insolubility in acids,
This assumption provided a convenient, logical explanation for the black powder's survival. The material was considered an annoying impurity, a useless terrestrial dirt that simply required mechanical filtration to be removed from the valuable platinum solution. The transition of this black powder from an industrial nuisance to a recognized fundamental element was orchestrated by the English chemist Smithson Tennant in 1803. Tennant possessed a methodological rigor that rejected superficial assumptions, determining that the extraordinary density of the black residue was entirely inconsistent with the relatively light atomic mass of carbon-based graphite. He initiated a systematic chemical assault on the powder, seeking to find a reagent capable of breaking its profound thermodynamic stability. Recognizing that the strongest acids had failed, Tennant reversed the chemical approach, utilizing a process of extreme alkaline fusion. He mixed the black powder with sodium hydroxide, NaOH, and sodium nitrate, NaNO3, placing the mixture inside a silver crucible and subjecting it to the intense, continuous heat of a red-hot furnace. This alkaline fusion represented a thermodynamic environment drastically different from the acidic bath of aqua regia. The extreme heat, combined with the presence of the nitrate oxidizer in a highly basic medium, provided the exact activation energy required to breach the defensive electronic shielding of the mystery atoms. Under these conditions, the unyielding metallic lattice of the black powder finally collapsed, and the metal atoms bonded with oxygen to form a water-soluble oxide complex.
When Tennant subsequently cooled the crucible and dissolved the resulting mass in H2O, he had successfully forced the indestructible powder into a liquid solution. The subsequent stage of Tennant's analysis revealed a visual characteristic that proved he had isolated an entirely new class of matter. When he began to slowly neutralize the highly alkaline solution by adding hydrochloric acid in precise increments, the liquid did not maintain a uniform appearance. Instead, it underwent a series of dramatic, highly saturated color changes. Depending on the exact concentration of the acid and the degree of oxidation, the solution transitioned through vivid shades of dark red, brilliant green, deep blue, and deep purple. The mechanism governing this spectacular optical display relies on the principles of transition metal coordination chemistry. As the unknown metal atoms bonded with varying numbers of oxygen and chloride ions, their outer electron orbitals were physically distorted. The energy gaps between these distorted orbitals dictate exactly which wavelengths of visible light the electrons can absorb. When white light passes through the solution, specific colors are swallowed by the electrons jumping across these specific energy gaps, and the remaining unabsorbed wavelengths pass through to the observer's eye. Because the metal formed multiple distinct coordination complexes, each with a different orbital geometry, it acted as a variable filter for the visible spectrum. Recognizing that this unprecedented array of colors was the defining diagnostic signature of the new element, Tennant named it iridium, deriving the title from Iris, the winged goddess of the rainbow and the messenger of the Olympian gods in classical Greek mythology. Despite the elegance of its discovery and the poetic nature of its name, the isolation of iridium triggered a prolonged era of profound engineering frustration. Tennant had successfully proven the existence of the 77th element and documented its chemical properties, but the physical reality of the metal in its pure, solid state presented an insurmountable barrier to 19th century industry. The newly named element proved to be far easier to locate than it was to manipulate. The primary obstacle was the element's staggering thermodynamic resolve. To utilize a metal for structural or mechanical purposes, engineers must first melt it to cast it into a uniform shape. The standard metallurgical furnaces of the 1800s, fueled by coal and amplified by mechanical bellows, could achieve maximum operating temperatures of roughly 2,500 degrees Fahrenheit. While this was sufficient to melt iron, copper, and even gold, it fell drastically short of the thermal energy required to disrupt the atomic lattice of iridium.
Iridium possesses a melting point of 4,435 degrees Fahrenheit. When a solid sample of the metal was placed in the most advanced crucibles of the era, the intense heat of the coal fires had absolutely no structural effect. The thermal energy transferred to the iridium lattice simply caused the atoms to vibrate in place, falling woefully short of the kinetic threshold necessary to break the metallic bonds and induce a liquid state. To the frustrated metallurgists attempting to work with the material, trying to melt iridium with a coal furnace was analogous to attempting to melt a piece of granite with a single candle. It was an exercise in thermal futility. The secondary obstacle was the metal's extreme mechanical inflexibility at room temperature. In traditional metalworking, if a material cannot be melted, it is often shaped through the application of brute physical force, utilizing the techniques of the blacksmith's anvil. Metals like iron and gold possess crystal lattices containing slip planes, specific geometric alignments where layers of atoms can smoothly slide over one another when struck by a hammer, allowing the metal to bend, flatten, and stretch without breaking. Iridium, however, completely lacks this atomic compliance. Its incredibly dense, face-centered cubic structure is locked in place by highly directional electron bonds that strictly forbid any atomic sliding at ambient temperatures. When an engineer attempted to flatten a piece of solid iridium with a heavy steel hammer, the metal did not yield or deform. Instead, the mechanical stress exceeded the cohesive strength of the grain boundaries within the crystal, causing the iridium to fracture and shatter into jagged crystalline shards, much like a piece of dropped glass. This combination of an unreachable melting point and an absolute lack of malleability rendered iridium functionally useless for several decades following its discovery. It occupied a bizarre position in the hierarchy of materials. It was significantly rarer than gold, denser than lead, and more resistant to corrosion than platinum. Yet it could not be cast into a coin, drawn into a wire, or forged into a vessel. It became the most expensive and unworkable black sand resting on the shelves of European laboratories, a substance of extreme theoretical interest but zero practical application. It was an element that categorically refused to adapt to the limitations of human technology. The resolution to this historical drama required a fundamental shift in engineering philosophy. Instead of attempting to force iridium to behave like a conventional workable metal, inventors realized that its absolute refusal to yield was, in fact, its greatest asset.
In the mid-19th century, pioneers in the manufacturing of high-quality writing instruments, such as John Isaac Hawkins, began to utilize the raw, unmelted grains of iridium alloys exactly as they were found in nature. By carefully selecting microscopic, naturally occurring nuggets of osmiridium, an incredibly hard native alloy of osmium and iridium, and soldering them directly onto the tips of gold pen nibs, they bypassed the need to melt or forge the metal entirely. These tiny grains were then shaped through slow, painstaking abrasion using diamond dust, the only material hard enough to cut the iridium. This innovation marked the moment when the useless dirt was finally recognized as the ultimate guarantor of physical permanence. The extreme hardness and chemical inertness that had frustrated metallurgists for half a century were exactly the properties required to create a writing instrument that would never wear down or corrode against the abrasive fibers of paper. The element transitioned from being a symbol of chemical stubbornness to the premier material for limit case engineering. The historical drama of iridium is the narrative of a substance that waited in the dark acid baths and the useless dust piles, remaining entirely uncompromising until human civilization advanced enough to require a material that was as immutable and enduring as the laws of physics themselves. It is the story of how a rainbow-colored chemical ghost forced humanity to stop trying to bend matter to its will and instead learn to harness the indestructible architecture of an element that refuses to change. The operational stability of the contemporary technological landscape relies upon a highly exclusive category of materials that perform their most critical functions in absolute obscurity. The 77th element, long dismissed by 19th century metallurgists as an intractable and useless black powder, has transitioned into the defining grey cardinal of advanced engineering. Iridium does not construct the visible frames of our architecture, nor does it flow as the primary current through our electrical grids. Instead, it occupies the extreme thermodynamic and mechanical margins of industry. It is deployed exclusively in environments where conventional metals, ceramics, and synthetic polymers would undergo immediate and catastrophic structural failure. The modern high-definition digital ecosystem, the efficiency of global transportation, and the localized eradication of cellular disease are all predicated upon the specific atomic architecture of a metal that categorically refuses to interact with its surroundings. To comprehend the hidden engine of the present era is to examine how the absolute introversion and thermodynamic resolve of iridium are harnessed to manipulate light, ignite fuel, and emit life-saving radiation with a precision that borders on the absolute. The most profound and ubiquitous application of this structural resilience is found at the very beginning of the supply chain for advanced optics and microelectronics. Every high-resolution lens in a modern smartphone camera and every solid-state laser utilized in delicate refractive eye surgery relies upon the existence of flawless, lab-grown synthetic crystals. These optical components are primarily composed of materials such as synthetic sapphire or yttrium aluminium garnet. To manufacture a synthetic crystal of this caliber, engineers utilize the Czochralski process, an industrial technique that demands the manipulation of matter at temperatures that challenge the limits of terrestrial engineering. The raw mineral components must be heated until they completely liquefy, creating a pool of molten optical glass that reaches temperatures exceeding 3,600 degrees Fahrenheit. Into this glowing liquid bath, a tiny, perfect seed crystal is lowered and then slowly rotated and pulled upward. As the liquid clings to the seed and cools, it mimics the atomic structure of the seed, slowly growing into a massive, flawless, cylindrical crystal. To explain the mechanical difficulty of this process through a domestic analogy, it is akin to attempting to draw a perfectly clear, solid icicle out of a pot of boiling water, with the strict requirement that not a single speck of dust or rust from the pot enters the water. The primary engineering bottleneck lies in the construction of the container, or crucible, that must hold this molten liquid. If a crucible were forged from high-strength steel or titanium, the vessel itself would melt and collapse long before the synthetic sapphire reached its liquid state. If a highly heat-resistant ceramic were used, the corrosive nature of the molten mineral bath would slowly dissolve the walls of the container. This would release microscopic trace elements, stray atoms of calcium or silicon, into the liquid. Even a single foreign atom incorporated into the growing crystal lattice acts as a microscopic defect, absorbing light and rendering the entire crystal useless for high-precision laser applications or high-definition photography. The only material in the human inventory capable of performing this task is pure iridium. Iridium crucibles, forged through complex powder metallurgy techniques, provide a thermodynamic and chemical wall that absolutely guarantees the purity of the crystal. Because iridium possesses a melting point of 4,435 degrees Fahrenheit, it can contain the violently hot molten sapphire bath while remaining entirely solid. Furthermore, the extreme density and immense binding energy of the iridium atoms ensure that the walls of the crucible do not shed a single particle into the liquid. The metal sits in a state of white-hot incandescence, its atoms vibrating furiously, yet it categorically refuses to yield to the thermal stress or react with the molten minerals it holds. Every perfect photograph captured by a mobile device and every precise laser incision that corrects a human cornea is the direct optical consequence of an iridium crucible functioning as an unyielding, incorruptible chalice.
This same principle of extreme endurance is deployed within the high-velocity, high-pressure environment of the modern internal combustion engine, where iridium solves a fundamental problem of electrical ignition. To maximize fuel efficiency and minimize harmful exhaust emissions, contemporary engines are designed to operate with highly compressed, lean air-fuel mixtures. This environment acts as a powerful electrical insulator. To force a spark of electricity to jump across the gap between two electrodes and ignite the fuel, the ignition coil must generate an intense surge of voltage. In standard spark plugs, manufactured from copper or platinum alloys, the electrodes must be relatively thick to survive the repeated ablation of the 10,000°F plasma arc. However, a thick, flat electrode spreads the electrical field over a wide area, requiring more energy to force the spark across the gap, which can lead to inefficient combustion and engine misfires. The engineering solution relies on the concept of electrical field concentration. To explain this on the fingers, if the flow of a river is forced through a wide open channel, the water moves slowly and with dispersed force. If that same volume of water is forced through a narrow, highly constricted nozzle, it emerges as a high-pressure, highly focused jet. In the realm of electromagnetism, a sharp, needle-like point concentrates the electrical pressure, making it significantly easier for the spark to jump the gap with maximum intensity. However, if a standard metal were machined to a microscopic point of 0.4 millimeters, the intense heat and explosive force of the plasma arc would melt and erode the fine tip within a matter of minutes. By laser welding a microscopic pad of iridium to the very tip of the central electrode, engineers can achieve the impossible.
The extreme hardness and unmatched melting point of the 77th element allow the electrode to be machined to an incredibly sharp, needle-like point that will not erode, melt, or blunt under the relentless assault of the combustion chamber. The iridium tip acts as an indestructible lightning rod. It concentrates the electrical field, ensuring that a powerful, perfectly timed plasma arc detonates the fuel mixture with absolute consistency, thousands of times per minute. This microscopic fragment of stellar shrapnel allows the engine to burn fuel more completely, significantly increasing gas mileage and reducing toxic emissions, while surviving the hellish interior of the engine block for over 100,000 miles of travel without requiring maintenance. The efficiency of the global automotive fleet is silently dictated by the refusal of this heavy metal to be blasted away by electrical fire.
Beyond the realms of optics and transportation, the dense, unyielding nature of iridium has been adapted to serve as a highly precise, localized weapon against cellular disease in the field of modern oncology. The treatment of malignant internal tumors often relies on radiotherapy, utilizing high-energy radiation to shatter the DNA of cancer cells and halt their ability to divide. The traditional method of external beam radiation involves projecting a lethal beam of energy from outside the body, through the skin, and into the tumor. The critical flaw in this approach is collateral damage. The radiation must pass through layers of healthy tissue and vital organs to reach its target, causing significant secondary injury to the patient. To bypass this biological shield, the medical community utilizes a procedure known as high-dose rate brachytherapy, which relies upon a radioactive isotope of the metal, iridium-192.
This isotope does not occur in nature. It is artificially manufactured by placing stable iridium-191 inside a nuclear research reactor and bombarding it with a stream of neutrons until the nuclei absorb an extra particle and become highly unstable. The resulting iridium-192 undergoes constant radioactive decay, emitting a powerful, steady stream of tissue-penetrating gamma rays. Because elemental iridium is incredibly dense, an immense amount of radioactive energy can be packed into a physical volume no larger than a grain of rice.
This microscopic seed of iridium-192 is sealed within a tiny, biocompatible capsule of titanium or platinum. Using a hollow delivery catheter and advanced computer imaging, a surgeon physically inserts this highly radioactive capsule directly into the center of the malignant tumor. To explain the physics of this targeted strike on the fingers, the radiation follows the inverse square law, meaning that the intensity of the gamma rays drops off exponentially as they travel away from the source. It is like placing a small, incredibly intense heater directly inside a block of ice to melt a specific, small cavity from the inside out, rather than aiming a massive flamethrower at the entire block from a distance. The iridium seed delivers a lethal, concentrated dose of gamma radiation directly to the cancerous tissue surrounding it, completely devastating the tumor's genetic architecture. Yet, just a few millimeters away, the radiation intensity drops to a level that spares the surrounding healthy organs. Furthermore, the absolute chemical inertness of the iridium ensures that the highly radioactive metal will never dissolve or react with the bloodstream or the acidic fluids of the human body in the event of a microscopic breach in the capsule. Once the precisely calculated dose of radiation has been delivered over a span of minutes, the iridium seed is retracted through the catheter and safely stored in a lead-lined vault. This medical application represents the ultimate realization of the element's character. The same unyielding property that frustrated the 19th century chemists who attempted to dissolve the black powder in acid is the exact property that ensures the safe delivery of nuclear medicine within the human circulatory system. Iridium is the grey cardinal of the modern era because it operates at the absolute boundaries of what physical matter can endure. It provides the pristine optical clarity of our global communications. It dictates the thermal efficiency of our combustion networks, and it acts as a molecular sniper in the fight against cellular decay. We do not see the 77th element, but our civilization leans its entire weight upon the microscopic points of this metal, trusting in the sheer, undeniable reality that when subjected to the most extreme heat, electricity, and biology on Earth, iridium will be the only material left standing. The capacity of the Earth to preserve a detailed historical record of its own biological and geological evolution is severely limited by the relentless and uncompromising laws of chemical entropy and tectonic recycling. The planetary surface operates as an immensely efficient grinding mechanism, where the corrosive presence of atmospheric oxygen, the universal solvent properties of H2O, and the continuous subduction of the continental plates act to erase the physical evidence of the past. When evaluated across a timeline spanning tens of millions of years, the vast majority of physical events are completely obliterated from the stratigraphic ledger. Whole mountain ranges are pulverized into microscopic grains of silica by the friction of glaciers, and immense biological ecosystems are reduced to unidentifiable carbon chains by the metabolic actions of subterranean bacteria. To permanently record a singular, instantaneous event of global devastation, the Earth requires a chemical marker that is entirely immune to the solvent properties of groundwater and the oxidative power of the atmosphere. The 77th element provides this exact function, serving as an indestructible atomic timestamp that separates the eras of planetary history with absolute physical authority. The most profound demonstration of this elemental endurance is found within a microscopic layer of sedimentary rock that records the most violent biological transition in the history of complex life. Approximately 66 million years ago, the trajectory of terrestrial evolution was permanently altered by the arrival of a celestial body, an asteroid estimated to be over 6 miles in diameter, traveling through the vacuum of space at a velocity exceeding 40,000 miles per hour. When this massive object collided with the shallow, carbonate-rich sea covering the modern-day Yucatan Peninsula, the physics of the impact transcended simple mechanical destruction. The kinetic energy of the asteroid,
which was equivalent to the detonation of 100 million megatons of TNT, was instantly converted into thermal and acoustic shock waves. In the fraction of a second following the impact, the localized temperature spiked to tens of thousands of degrees Fahrenheit, a thermal intensity that briefly rivaled the surface of the Sun. This unimaginable heat did not merely shatter the asteroid and the Earth's bedrock, it completely vaporized them, transforming millions of tons of solid rock into an expanding, superheated plasma. The chemical composition of the impacting asteroid was fundamentally different from the chemical composition of the Earth's crust. Because the asteroid was a primitive, undifferentiated chondrite, it had never undergone the planetary-scale melting process known as the iron catastrophe, which had dragged all the heavy, iron-loving elements into the Earth's molten core billions of years earlier. Consequently, the asteroid retained the original, primordial mixture of elements present in the early solar nebula, including a massive payload of heavy platinum group metals. Chief among these was iridium, an element that was practically non-existent on the surface of the Earth. When the asteroid struck and vaporized, its entire inventory of iridium was atomized and blasted into the upper stratosphere and low Earth orbit, mixing with the pulverized remnants of the terrestrial crust to form a dense, opaque global cloud. This atmospheric blanket of silicate dust, sulfur aerosols, and vaporized metal rapidly enveloped the entire planet, effectively blocking out all incoming solar radiation. The immediate consequence was the cessation of global photosynthesis, leading to the rapid collapse of the terrestrial and marine food webs and the subsequent extinction of approximately 75% of all plant and animal species, including all non-avian dinosaurs. However, as the atmosphere slowly cooled over the following months and years, a process of planetary-scale precipitation began. The vaporized elements condensed into microscopic droplets and began to fall back to the surface. The behavior of iridium during this global fallout reveals the extreme resilience of its atomic architecture. In the highly chaotic and corrosive environment of the post-impact atmosphere, which was saturated with acidic sulfur compounds and reactive oxygen species, most vaporized metals would have immediately formed complex chemical compounds or dissolved into the acidic rain. Iridium, possessing an absolute chemical inertness and densely packed electron orbitals, categorically refused to participate in these atmospheric reactions. It condensed into pure, microscopic metallic particles and settled evenly over the entire surface of the globe. To explain the mechanics of this event, it was as if an invisible, highly toxic metallic snow had fallen across every continent and every ocean, laying down a perfectly uniform blanket of star ash over the ashes of the dying biosphere. In the geological formations of the present day, this apocalyptic event is visible as a distinct, paper-thin layer of grayish-black clay that separates the older, fossil-rich Cretaceous limestone from the newer, comparatively barren Paleogene rock. This boundary layer is found in sedimentary outcrops all over the world, from the ocean cliffs of Stevens Klint in Denmark to the mountain gorges of Gubbio in Italy. For over a century, geologists observed this sudden disappearance of fossils in the rock record, but lacked the physical evidence to prove the mechanism of the extinction. The fossilized bones of the dinosaurs simply vanished at this exact stratigraphic line, leaving a mystery that biology alone could not solve. The resolution to this planetary mystery was provided in the late 1970s through the application of advanced nuclear physics, specifically a technique known as neutron activation analysis. Researchers extracted samples of the gray boundary clay and bombarded them with a stream of free neutrons inside a nuclear research reactor. When the stable atoms in the clay absorbed these neutrons, they became temporarily radioactive, emitting specific frequencies of gamma rays as they decayed. Because every element emits a unique gamma ray signature, The scientists could precisely calculate the elemental composition of the clay down to parts per billion. The analysis revealed a staggering anomaly. The concentration of iridium in the boundary clay was hundreds of times higher than the natural background levels found in any typical terrestrial rock. This iridium anomaly functioned as an undeniable chemical fingerprint. Because the Earth's natural iridium is locked 1,800 miles deep within the planetary core, the massive spike in the boundary layer could only have originated from a catastrophic extraterrestrial source. Iridium provided the absolute proof that a giant asteroid had struck the planet. If the asteroid had been composed entirely of iron, the evidence would have oxidized into rust and washed away into the oceans millions of years ago. If it had been composed of carbon, it would have burned into CO2 and been absorbed by the surviving plants. Iridium was the only element heavy enough to be a cosmic signature, dense enough to sink through the atmospheric chaos, and noble enough to sit completely unchanged in damp, acidic clay for 66 million years without losing a single electron. It serves as the ultimate indestructible marker of an ending and a beginning, silently dividing the era of giant reptiles from the subsequent rise of mammals. When projecting the trajectory of the current human era into the deep geological future, the 77th element takes on a new role as the definitive signature of technological civilization. Humanity has effectively become a geological force, actively mining the trace amounts of iridium left behind by secondary meteorite impacts and concentrating them through high-energy industrial processes. The natural distribution of iridium on the Earth's surface is a diffuse, microscopic dusting. However, human engineering has gathered these atoms and fused them into dense, highly specific geometric shapes. The microscopic laser-welded tips of high-performance spark plugs, the heavily shielded radioactive seeds used for targeted oncology, and the massive, indestructible crucibles utilized for growing synthetic sapphire crystals represent unnatural, extreme concentrations of the metal. As the current epoch inevitably transitions into deep time, the vast majority of human infrastructure will succumb to the relentless forces of entropy. The skyscrapers of carbon steel will dissolve into amorphous streaks of iron oxide in the soil, and the vast networks of copper wiring will turn into green, powdery salts. The silicon microchips will eventually be crushed back into the sand from which they were forged, yet the concentrated artifacts of iridium will remain entirely immune to this planetary recycling. When a spark plug is buried in the anaerobic mud of a landfill or the sediment of a flooded city, the iridium tip will not rust, corrode, or dissolve in the groundwater. It will remain in a state of pristine, metallic perfection, acting as a synthetic technofossil. Millions of years from now, if future geologists survey the sedimentary layers of the Anthropocene, they will discover a second iridium anomaly. Unlike the uniform global dusting of the Cretaceous-Paleogene boundary, this new anomaly will consist of localized, highly concentrated nodes of pure iridium scattered across the ruins of ancient urban centers. The discovery of these unyielding metallic cylinders and flawless crucibles will provide absolute physical proof that a species once existed capable of identifying, extracting, and shaping the most indestructible material in the periodic table. Iridium will serve as the final, untarnished archivist of human capability, a silent metal witness that will outlast our languages, our biological descendants, and our deepest digital records.
The absolute permanence of this element is ultimately bounded only by the life cycle of the solar system itself. In approximately 5 billion years, the Sun will exhaust its primary supply of hydrogen fuel and begin the transition into a red giant. As the solar atmosphere expands to engulf the inner planets, the surface temperature of the Earth will climb steadily, eventually exceeding 4,435 degrees Fahrenheit. At this extreme thermal threshold, the invincible nature of the 77th element will finally be overcome. The iridium artifacts buried in the crust, the microscopic tips of the spark plugs, and the ancient dust of the asteroid that killed the dinosaurs will reach their melting point. The solid metal will liquefy, merging with the global ocean of glowing, churning magma that will consume the planet. As the Earth is eventually vaporized by the expanding sun, the iridium atoms will be liberated from their terrestrial confinement. They will be transformed into an atomic gas and swept outward by the intense solar winds, returning to the cold vacuum of the interstellar medium. This return to the void represents the closing of a massive cosmic cycle. The heavy, unyielding atoms that were forged in the apocalyptic collision of two neutron stars drifted through the galaxy for eons, plummeted into the Earth to extinguish a biological era, and were later shaped by human hands to spark engines and cure disease, will drift through the darkness of space once more. Because iridium is a stable, non-radioactive element, the atomic nuclei will remain entirely intact. They will continue to exist as the same dense, heavy particles they were at the beginning of their journey, carrying no memory of the dinosaurs they buried or the machines they powered. Iridium is the ultimate cosmic traveler, a material of absolute physical standards that simply passes through the history of the Earth, remaining entirely unbothered by the chaos of biology or the rise and fall of civilizations. It is a shimmering, indestructible thread that connects the violent physics of a dying star to the final, fiery evaporation of our world, proving that in a universe defined by constant transformation, the most profound stories are told by the materials that refuse to change.